Very good. I already created a page about yourself. Well, it is a real pleasure to introduce today's speaker, Lily Su. She is the Sun Wu Assistant Professor in the Department of Industrial Engineering and Operations Research at Columbia University. And her work is really cool and amazing. She's working in the intersection of machine learning, optimization, and causal inference with a clear focus using AI to support real high-stakes decisions in planetary health from the biodiversity conservation and climate and public health. Lily has so many things that she has done, and she has been recognized in many different setups. Her contribution has been widely recognized by the Google PhD Fellow, by the Civil Scholar, winner of the Informs Doing Good with Good competition, and runner for both from the AI Best Paper Award and the IFAAMAS Victor Lesser Distinguished Dissertation Award. She has been recognized in the EAAMO community, and in reality, she's an amazing person that she was very quickly to respond to my invitation. That's I really appreciate it. And today she's going to be discussing about how we can go beyond AI for prediction and how AI can actually guide a better decision for the planet. Thank you, Lily. I really appreciate that you are joining us, and the floor is yours.
Perfect. Thank you so much, Otto, for the invitation. It's really a pleasure to be here, and I'm very happy to keep this conversational. So feel free to interrupt me at any stage. But my work is largely motivated by all sorts of challenges facing our planet, from biodiversity loss to climate change, public health challenges like maternal mortality and food insecurity. And the view I try to take is recognizing that all of these challenges are interlinked. So biodiversity conservation, for example, is an essential tool in our fight to combat climate change, as nature-based solutions can contribute up to 37% of CO2 emissions necessary to halt climate change and meet the Paris Agreement. And then climate change is currently exacerbating the biodiversity crisis by stripping species of their climatic habitat range. So it's important to think about the interrelationship between all of this. And planetary health gives one lens into looking at the relationship between human health and health of our planet, and how both of these are intimately related to each other. So I'll give a little bit of an overview here of my work on both ends of this. On maternal health care, working on intervention planning for expectant women in India, and biodiversity conservation on helping developing AI tools to help plan patrols to prevent poaching and protect biodiversity. And the key question across this is that one of how to optimally allocate limited resources. So if we are in some state of the world and we want to design an ideal intervention to take us to a better state, the kinds of variables we would be interested in are like, what are the density of animals? What is the health status of something? We want to make sure that this gets into a better state. Measured by some objective. So putting this into terms that we're familiar with from reinforcement learning, the key characteristic of so many of these problems is that we often are dealing with these sequential decision-making problems, but with many, many challenges along the way. So our data is incomplete. We have very complex, often combinatorial actions. We have long planning horizons that we have to plan over. We have high stakes rewards, so we really have to think about how to do the best with limited information. And the types of questions that my work thinks about is learning what these state variables are, planning and determining best actions, evaluating the impact of our action on the next state, using causal inference to help us infer what these transition dynamics can be, and then working with partners to bridge this gap between theory and practice. And across the spectrum on this pipeline from data to deployment, I'll be talking about my work in online learning, figuring out how to bring in domain knowledge from the problem setting so that we can converge faster with less data required, on how to do planning in certain settings where we have a lot of uncertainty so that we can make robust decisions that are tractable at scale. causal inference to help us understand the effectiveness of our actions, by also integrating machine learning in the process to help us overcome gaps in the missing data, and then working with partners to deploy this work more at scale. So another aspect of my work that I want to highlight is that I really try to do practice-driven research that is closely embedded with the communities that are really doing the work and also impacted by this work. So I've had the privilege of going on field visits to multiple different sites across Cambodia, Belize, and Uganda. So the first bit that I'll be talking about today is really focused on this angle of biodiversity conservation, and then I'll talk about some work on maternal health afterwards. So to motivate the biodiversity crisis that many of you might already be aware, we've seen around a 70% decline in the average population size of vertebrate species since 1970. So it's been a dramatic decline, and the UN has estimated that there's now 1 million species in danger of extinction. And one of the biggest threats against biodiversity is poaching, where people will come into animal habitats, even in national parks and other kinds of wildlife sanctuaries, and place a bunch of traps meant to catch animals. So here is a photo from an article in The Guardian of a team of rangers in front of this mountain of snares that were removed from the park. And every single little wire circle that you see here was a trap meant to catch animals. And this is the scale of the poaching problem in Murchison Falls National Park. So ecologists have estimated that there's about 4 snares for every square kilometer in the park. And this is a very large 5,000 square kilometer park. So that's about 20,000 snares. But there's unfortunately only 250 rangers that are available to conduct patrols. So it's a huge challenge of limited resources. And the question is, how can we develop more sensible tools to help us inform this kind of decision making? So to just walk through the model of this problem, so we have some kind of protected area that we discretize into a set of n regions. So each of these refers to like a square kilometer area of the park. And there are some associated covariates for each region, like we have geographic information about the land cover and how far we are to the nearest road. And the action that we want to determine is how to effectively plan patrols over a subset of those regions, subject to a budget constraint. So we might only have 40 hours a week that were available to plan patrols. And our goal is to maximize the expected number of snares removed. But exactly where the snares are is unknown. So here's the challenge of learning, of how do we figure out, how do we fill in this? So in this work, we're really focused on this learning component, and we'll also discuss how to do planning along the way using multi-armed bandits. Aldo, did you? No. Okay. Sorry, I thought I heard something. And the key trade-off here is how to navigate between exploration and exploitation, of exploring areas where we haven't really spent time before. We don't really have a sense of like what the data quality is there. We don't really know what the threats are in those places. And also exploiting areas that we've already seen. So we don't want to spend too much of our time exploring areas of uncertainty, and because we don't want to neglect the areas that we already know to have high poaching risk. So the model that we take here is that of multi-armed bandits, and I'll give a quick overview of this form of machine learning. So in a multi-armed bandit for online learning, we think of each arm in the problem as an action. So the action could be to patrol region 1 or region 2. And we keep track of our estimate of what the reward is at each region. And we can also keep track of our confidence interval of whatever this prediction, of how good our prediction is. And following a key principle in multi-armed bandits, which is optimism in the face of uncertainty, this means we want to take the action that has the highest upper confidence bound, looking at our confidence interval, because this region either has the opportunity to have really high reward, in which case here, this refers to the probability of having snares and having this poaching threat. Or at the very least, even if we don't have good reward, then we'll reduce uncertainty to improve our model in the future. So it's really dealing with that trade-off between what is the best kind of myopic action that we can take now versus how do we think about what's most beneficial in the long run. And please note that even if the empirical mean of region 1 is lower than that of 2, we might still prefer region 1 because its upper confidence bound is higher. So that's really the intuition behind this algorithm. And in this case, we would take an action on region 1, we would collect some data that would reduce our uncertainty, and we would continue doing so until the upper confidence bound of this region is lower than that of region 2. So a key challenge here, though, in the context of patrol planning and biodiversity conservation is that of imperfect observation. So for an area that we don't visit, we have no idea what the threats are there. We have no idea what the poaching probabilities are. But this is normal for online learning. This is known as bandit feedback, where we don't get any observations for actions we don't take. So this is just, talking about how difficult it is, how costly it is to even collect data and improve our models. But an additional challenge that we face in this context is even for regions that we do patrol, if we observe a snare, then we are confident of the true label. It's 1. We know that it's a positive label. But if we don't observe a snare, there's uncertainty as to whether it's a true negative label. So we're in this case of positive and unlabeled data, because we're never confident that the negatives are true negatives. But the insight that we can bring in from this domain is recognizing that the probability of detecting a snare really depends on how much effort that we put in. So here I'm visualizing the relationship between patrol effort, like how much time that rangers spend, and the probability of detecting a snare for 25 different regions in the park. And what we find is that when rangers put in more effort, the probability of finding a snare goes up, but it has diminishing returns. And there's kind of a point at which this plot saturates. So even if we were to put in a lot more effort, we would not be more likely to find a snare. And what this tells us is we can kind of use the amount of effort as a proxy for the reliability of our negative label. So if we see a negative label with 0.25 patrol effort, then that doesn't really help us much. Maybe it's a positive, maybe it's a negative, we really don't know. But if we have a negative with 3 kilometers of patrol effort, then we can be much more confident that that indeed is a true negative label. Okay, so now what this tells us is that it's really important not just to think about where we go, but also how much effort we're spending in each region. And what we want to do, therefore, is find an allocation of patrol effort subject to an overall budget constraint. So this effort tells us how much time or effort to put in each of these N regions. And if we were to look at, some problem set with N regions and M discrete levels of effort, we can think about the complexity of this planning problem. And one challenge is scale. So this is a very large combinatorial action space where even if for some small number of levels of effort, like 10, this problem size could easily be 10 to the power of 100, which is just absolutely unfeasible. And the second aspect is that we have a very high stakes setting where, due to the importance of this problem setting, we can't afford to spend an excessive amount of time exploring. So if we did that, then we would just have animal populations completely go extinct. So we have to make sure that we're balancing this exploration and exploitation and minimizing our amount of unnecessary exploration as much as possible. So we'll talk about how we can integrate information from this problem setting to help us address both challenges. So the first is that we have decomposability in our action space. So the reward for an overall action, which is this vector beta, an allocation of patrol effort, can be decomposed into the sum of rewards at each region. So this is a very basic principle that our reward just has this additive structure. But what this enables us to do is instead of planning over this like exponential number of possible actions, we can break down our action selection problem into a set of 4 different regions, and then we can think about what is our expected reward for allocating different amounts of patrol effort for each of those. And now we can make estimates of our expected reward or this upper confidence bound for n times m number of regions instead. So now we only have like a linear number of reward estimates that we have to keep track of m times n number of estimates, rather than this exponentially large m to the power of n. And then I'll talk about later how we use optimization to help us select the best overall action given these smaller estimates. So our second challenge is that we are in this high stakes setting and we can't afford to do excessive exploration. So here's where we can bring in, again, problem structure to help us. So if we look at this probability of detecting a snare as a function of our patrol effort, this gives us a sense of what our reward function looks like, because the reward we get is finding a snare. So with this reward function, we can make a few observations that, one, this function is monotonically non-decreasing. So as we exert more effort, we're never going to be less likely to find a snare. That this problem is fairly smooth. So there's Lipschitz continuity with some Lipschitz constant L that bounds the maximum derivative of this problem. And then we have very intuitive. If we exert no effort, there's no probability of finding a snare. So this 0 equals 0 assumption also helps out. Okay, so now we've made these estimates of how much reward we expect to get. What's the probability of finding a snare if we patrol these different regions with different levels of effort? But how can we do better? So what we can recognize is if we just zoom in on one region, and let's say we have a really good estimate for how likely we are to find snares at 3 kilometers of effort, that gives us some understanding of how likely we are to find snares at different levels of effort too. So let's unpack that. So I'm going back to this example where we have 2 different arms, A and B, and for every other level of effort, this means that we don't know what the reward is. We don't know what the probability of finding snares is. So those values could be anywhere within this green region. But based on the domain knowledge that we have from this problem structure, we can enhance our learning. So the first is incorporating Lipschitz continuity, recognizing that the change in our reward function will be constrained by how much we change the level of effort. So this gives us an upper bound on how high up this our uncertainty bounds can be. And that enables us to prune a lot of the space of uncertainty so that we can spend much less time exploring. The second aspect we have is that the knowledge that 0 effort leads to 0 probability of finding a snare. And this, when combined with the Lipschitz continuity assumption, gives us a really powerful approach to reduce our uncertainty here. And the last aspect is monotonicity. So our reward functions are monotonically non-decreasing. So if we have an estimate of the upper confidence bound at 3 kilometers of effort, that gives us an upper bound as well at any lower level of effort. So monotonicity helps us further reduce our uncertainty. And all of this combined dramatically reduces the space that we have to explore. So instead of putting a lot of effort to collect data and learn different types of actions, we can dramatically reduce the amount of data collection that we need so that we can more quickly move to exploiting and taking good actions. Okay, so now we have more tight estimates of the rewards for different actions for one region. And we can also think about now how we can apply this knowledge to other regions, recognizing that these aren't just like arbitrary actions, but rather they're each region corresponds to a physical location in the real world. And there's additional covariate information that we have about those regions that we can then transfer and apply towards each other. So what we have now is we have good estimates of the reward at one region, and this can lead as well um, to transferring knowledge to another region. So let's imagine that there's a second region too that I haven't patrolled yet. So I don't know anything here. And the only information that I have at the moment is this knowledge that zero patrol leads to zero effort. But if I could quantify the similarity between these two regions, let's say that they differ only by elevation, by 100 meters. So then that delta difference between these two regions also gives me a distance that I can apply my Lipschitz continuity assumption to as well. And I could transfer knowledge from one set of regions to another. And that enables me to further reduce my uncertainty space. So with all this out together, now I have estimates of the expected reward within different regions at different levels of effort, and I can bring that all together to actually determine now with all these estimates, how do I transfer this into an action? So to take all my estimates to select an overall action, my objective is to maximize my sum of upper confidence bound values subject to my budget constraint. And note that this problem formulation is very flexible, so I can bring in other estimates, other constraints as well. So if I had path constraints or if I had scheduling constraints, all of those could be embedded additionally as further constraints within this mixed integer linear program. And then overall, this gives me an allocation of which regions to select, which regions to patrol at what levels of patrol effort. And we also have some theoretical results that just tells us like how good our algorithm is expected to perform for a general type of multi-arm bandit problem with this Lipschitz reward structure and combinatorial action structure. And to just kind of quickly talk through this, the regret of an online learning algorithm is defined with respect to whatever an optimal action would be. And therefore, we want the regret to be as small as possible, because if the regret is zero, that means we were taking the optimal action as if we had full information of the problem space. So unfortunately, our regret is not zero, but let's see how small we can make it. And the regret can be broken down into two terms, which is the discretization error and the selection regret for not picking the optimal arm. And the bottleneck is really the discretization error. This is the term that is linear. And the intuition now is if we reduce our discretization, then we have a smaller discretization regret, but we have more arms that we have to explore. So we would want to have a smaller delta, discretization gap, if we either had a longer time horizon or fewer regions or a bigger Lipschitz constant. And in practice, what we can do is set delta adaptively over time. So it starts off very coarse and then gets smaller and smaller over time. And then to make the math work out cleanly, this is the schedule that we can use, where every this many number of time steps, we divide our discretization in half. And then overall, what this gives us is the following regret bound. And the result is that compared to a Lipschitz bandit that ignores the combinatorial action structure that may be present in problems, we can reduce our regret bound from something that will grow with a number of regions to something that is fixed to be sublinear on the order of t to the 2/3. And we also have some empirical results that evaluates how good our action is using real data from a patrol planning problem in Cambodia. Okay, so please feel free to interrupt me at any stage, but otherwise I'll keep going. Okay, and then I'll just talk quickly about some extensions of this work too. So in the first paper, we're thinking about how to extend this patrol planning problem from looking at just planning over these regions and trying to maximize the expected number of snares that we're going to get to thinking about what our underlying objective is. And the underlying objective that we have is really trying to maximize protection for the species of highest concern. And it might be the case that maybe in one problem setting, there are more people who are focused on bushmeat hunting and really looking for deer rather than the most high value, most endangered species like elephants. So in that case, we might want to prioritize areas that have more elephants, even if they aren't the ones that will explicitly maximize the number of snares that we'll have. So this is just an example visualization of this. And then in our 2022 paper, we extend this work into designing a multi-objective reward function that will help us navigate this trade-off between maximizing snare removal versus maximizing this prioritization over different kinds of species. And then in a preprint that is still under review at the moment, we are thinking about how to optimally integrate historical data, recognizing that bad samples can require arbitrarily large space and commute. So this is thinking about how do we do online machine learning in a setting where we already have some data, but that data is really imbalanced. Maybe not all of it is good quality. And the meta algorithm that we propose here is called artificial replay, which provides us a very kind of useful heuristic algorithm of how to best integrate the minimum amount of historical data necessary to still achieve maximal results. And there's some theoretical results in that paper as well. But now I'll move on to the next aspect here. So really thinking about how can we act dynamically within these problem settings. Because the assumption we've been making so far is that we might be in a noisy problem setting, but the poaching probability remains fairly static. But we're missing out on the fact that poachers are also strategic agents and they might change their behavior based on what we're doing. So we have to think about this now like a game theoretic interaction between rangers and poachers. And what we do is first validating with historical data from 2 parks in Uganda. We see that this assumption does hold, where if we patrol more at one region, then the probability of poaching in that next time step goes down. So poachers are indeed deterred by our actions. But if we have some estimate about how much they are deterred by, let's say we estimate 17% reduction in poaching probability, because our data is imperfect, again, that's like the key challenge I really want to emphasize, like we rarely lack perfect models of the world. Because our data is imperfect, we can't be confident that this is going to be a precise number, 17. But instead, we can be more confident that it falls within some kind of uncertainty interval. So let's say this value falls between 12 and 23%. So now the question is, how can we do planning that is robust to this uncertainty? And the objective that I want to argue for is that of minimizing the maximum regret, which contrasts to the standard notion in sequential planning, such as reinforcement learning, of maximizing the minimum reward. And let me try to convince you that minimax regret is a better objective. So I am specifying some parameter that we're uncertain over, and let's pretend that this z value takes on 3 values, 0.12, 0.17, or 0.23. We don't know which value is going to take on. So we can evaluate what is the best sequential policy that we could take in each of these settings using reinforcement learning, for example. And this gives us some upper bound on what the optimal reward could be in each instance. And we can also evaluate what the worst possible policy would be and how poorly we would perform. And this gives us a lower bound on our potential reward. And therefore, the space in between this upper bound and lower bound is really the gap in our decision quality. And this shows us the kind of like space over which we have agency. And zooming in on this, if we now think about taking a single fixed policy and applying this to all 3 problem settings, we get some amount of reward in each context. And the standard notion for robust planning with reinforcement learning is maximizing the minimum reward. And the case with minimum reward is this first instance. So our objective will tell us, okay, let's try to make our reward better in this context. But you see that our ceiling is really low. Like there's only a little bit of improvement that we can gain. So this maximizing the minimum reward objective can be overly conservative by focusing all of our efforts on this worst case scenario and neglecting the other scenarios. But instead, if we look at the quality of our decision, looking at regret with respect to some optimal action, that looking at regret and the setting where we have the maximum regret is really this third instance where there's a big gap between our performance and what the ceiling is. So this min-max regret objective, I think, is a much more reasonable notion of robust planning because it really thinks about the decision quality, how good we're doing relative to the counterfactual of what we could be doing. And I feel like this is a more reasonable notion of robust planning. But if you are in agreement with me that this is a natural objective to use, let's talk about why it's hard. So I'm writing out our objective, which is to find some policy pi, mapping from states to action, that minimizes the maximum regret we could incur over any environment parameter z. And regret is defined as the difference between the reward that we get from following our policy pi to the reward of an optimal policy, some pi star that is optimal for the true environment. But this was a really hard objective to solve for because pi is a sequential and continuous policy, so it's very complex and big. Z could be continuous and it could be multiple dimensions. So Z could also be a very large search space. And then the really tricky thing here is the regret objective has to be defined with respect to some optimal value that depends on Z. So anytime we change Z a little bit, the optimal policy for Z also changes. So there's really an underlying maximization problem. So we have to find some policy pi that minimizes regret for any environment parameter Z, and then we also have to compute what the optimal policy pi star would be for that Z value. So it's a really difficult problem. And I think that's why this objective has not really been considered for reinforcement learning previously. And the way that would make this problem tractable is by formulating it as a two-player zero-sum game, where we're slowly kind of going back and forth and building up this problem. And finding like the most optimal way to search across this very large space of different pi values and different Z values to find an optimal strategy. And in our paper, we prove that this approach also converges to a policy that is within epsilon of optimal. Okay. The last bit that I want to talk about here is really thinking about evaluation. So we've taken some action and we want to understand how good did it do and what is really distilling the benefit of our action compared to what natural changes would be evolving in the ecosystem anyways. So we had looked at this question for our robust reinforcement learning aspect. And now what we want to dig into further is really trying to understand, like, can we more precisely attribute causal impact of our actions on future poacher behavior? And this would be extremely powerful because it would enable conservation managers to go to the government or go to funders and say, like, we were able to bring down poaching by this amount. It's extremely significant. We need to continue funding this. But it's really hard to answer such questions in these contexts because, one, we can't conduct a randomized control trial. So what we do instead is leverage observational data as a quasi-experimental setting by identifying a past event which created a shock that enables us to kind of control for potential confounders. And the second key challenge that we have to overcome is, again, this challenge of imperfect observation in our data. So the outcome variable that we're trying to assess, which is poaching outcomes, is not perfectly observed. because of this, the uncertainty in our negative labels. So what we provide is a Bayesian model and machine learning to help us impute those missing outcome labels. And together, it's really thinking about how machine learning can help us fill in gaps in our understanding, so that we can come to this like better conclusions and provide more evidence towards the kinds of questions that are most relevant for policy. And I'm not going into detail here, but overall, what our work provides is the first causal evidence of deterrence in the context of poaching, where we show that for the average site in Murchison Falls National Park in Uganda, if rangers patrol a typical amount, the probability of poaching is about 21%. But if they patrol for an additional kilometer beyond typical levels, that poaching probability decreases by about 45% to 12% probability of poaching, which is a very significant reduction in poaching probabilities. So we're very excited about this result and hope that it could be valuable as a form of evidence to be brought into justifying the value of this work on the ground. Okay, so that's really what I had for the. Okay, and maybe I'll talk about this deployment stage, and that will kind of end what I wanted to share about conservation. So, um, we've spent all this time like working in this problem setting and trying to analyze this data and develop models, but we really want to understand how can we translate these ideas into impact on the ground. And to do this, we implemented a series of field tests in a number of sites, but I'll talk about our work in Cambodia. So Sri Pag Wildlife Sanctuary is a large protected area on the eastern boundary of Cambodia, adjacent to Vietnam. And at the beginning, when we were just developing machine learning predictive models of poaching threat, we wanted to understand first, do our predictions work? Are we able to identify poaching hotspots? And second, how do we actually translate these recommendations into actions that rangers can take? And to do so, we implemented a series of field tests where we selected from among all of our predictions a random subset of areas that we predicted to be high risk of poaching, and then also medium and low risk of poaching, and asked rangers to patrol each of those for a period of time. So this ran over the course of a 5-month field test, and what we found is that rangers did indeed find many more snares in the areas that we predict to be a high risk of poaching than medium or low, showing that our model is able to really discriminate between relative levels of poaching threat. And in a separate month where we were focused on patrolling high risk areas, they found over 1,000 more snares than they did in a typical month, which we thought was very compelling evidence. And we were thrilled to also get this positive feedback from our partners at WWF saying, I'm very excited with the results. Let's get this going on other countries too. So that's what we've spent a lot of time working on. In collaboration with SMART, which is a consortium of 8 different conservation organizations. They're focused on bringing protected area management to scale. And SMART provides a lot of software tools for park managers, including a phone app that rangers use to track all of their patrols, but then also a desktop software that managers will then use to analyze this data. So what we were able to find is that we built in a plugin for our system so that this can automatically, our predictions can be automatically run on the platform that they're already using. So this is really trying to find like the most frictionless path forward so that we're not relying on them to like learn new infrastructure or change the way that they collect data, but really trying to build in our systems to be as useful as possible. And these predictions have been in use throughout Central America, Africa, and Southeast Asia, where we've had the privilege of working with a large number of different organizations. Okay, so that's what I wanted to share about conservation, and I'm also happy to spend a few minutes talking about maternal health as well, but I'll pause there for any discussion or questions that you all might have.
Any questions?
Harry?
Yeah. does your model presuppose that the poachers have absolutely no knowledge of the strategies that you're implementing?
Correct. Yes, we are assuming like the first model that I presented where we apply this like online machine learning approach is assuming that poachers will like have similar patterns over time, and it's just a no we're just taking noisy samples from that. But in the second model, in the robust planning one, assumes that poachers are reactive, but they're not game theoretic. Like they're not like the highest level of strategic agent. And the
Mhm.
reason we make this assumption is because instead, if we were to formulate this problem as like a fully game theoretic setting where poachers are best responding to our actions, we think that the assumptions are way too strong because that would require that they have knowledge of the action that we're going to take, like where we're going to be patrolling, and then they will perfectly respond
Right.
accordingly. But we think that assumption is too strong because first, like as rangers, we don't even know exactly what poachers are doing, so we think it's unreasonable that they know exactly what we're doing. But second, poachers are very decentralized, so there's many different people who are out there poaching, and for the most part, they don't communicate, they don't coordinate.
Mhm.
Um, so we think that the behavior will be therefore like much more diffuse rather than kind of like coordinated and strategic.
So you don't have a master poacher guiding it all.
No,
Yeah.
no.
All right. Thank you.
Yes, great question. Vito?
Hi, thanks. Um, I was a little bit late, so apologies if you covered this earlier. Um, how do you account for corruption on for the Rangers? And have you thought about maybe using this to like estimate corruption? Because I
Yeah,
imagine that's a big issue
yeah.
here.
That's a really good question. I'm curious if you like maybe this is not work that I this is not an area that I know very well, but maybe you know more about corruption. Like I don't have a good sense of like how we would model corruption. Like, there's I guess there's many forms. Like there's corruption of they don't do what we're telling us to do. There's corruption of, oh yeah, they pretend like they're patrolling and they're really just kind of like sitting out there, just hanging out. Or the worst case is if um they are communicating and colluding with poachers and then therefore like intentionally going to places that poachers are not going. And I don't know, I don't have any immediate ideas of how we would try to identify any of those. But
Yeah, I mean, it's not something specifically that I study. But I was thinking just kind of along the lines of like if you're estimating things like um, uh, the 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 effect of patrolling in certain areas, and you're noticing things that are where you're expecting to see that effect, and you're not seeing it. It might point to corruption in the patrols.
I see. Yeah, I guess it's just hard to disentangle like what outcomes we would expect to have that fall short as a result of like what the rangers are doing or as a result of just environmental variation. Because
Mm.
like if they're finding fewer snares, maybe that's a good sign that they're actually extremely effective and they've brought down the level of poaching rather than oh they were just lazy and like not doing what they're supposed to do. Or maybe it just happened to be like a really rainy season, and therefore just like fewer people were out there and active. So there's that's really like one of the key challenges and something that I want to like emphasize like a really valuable part of where like AI can help as part of this process of really trying to help in causal identification and like disentangle the aspect of what is it that we're doing versus like what changes can be explained as a result of our actions versus just exogenous variation in the environment.
Cool. Thanks.
Yes. Jason?
Jason.
Yeah. Hey, Lily, thanks so much for the presentation. Really appreciate the topic, the content, and the delivery really worked.
Thanks
Appreciate
so
it.
much.
And thanks to Aldo for facilitating. I have a comment and two questions, and the questions are entirely unrelated. The first comment is, it sounds like what Vito's asking is just a different question that could be addressed through minimizing risk.
Yeah.
And it's really a fascinating spin, a different question for the same type of process that you've conducted. And I can see the massive opportunity and capability potential in what you've described, Lily, and how we can address other questions and problems using that suite of models.
Yeah.
I guess a question, and I may have missed it, was it seems like, and I'm wondering if folks are already doing this, but if you could address, so for example, if rangers are in the field and looking for snares and picking up snares, and if they are marking a GIS location, and if those results can be updated real time so that they can make a better, idea of where to go next. It looks like you're nodding, and that's already happening.
Well, that's a great question. And I will emphasize that like different protected areas have extreme like set of heterogeneity in their resources and technical capabilities. In the vast majority of cases, like these are like very remote wilderness, and they don't have connectivity on the internet. There's like, very sporadic like satellite connectivity, and a lot of sites don't even have like phones that will connect to satellites. So for the most part, that kind of like real time information is simply not available to us. And oftentimes there's even a further lag in data connection. So like most of the time they're collecting this data on like offline phones, and then they have to finish their patrol. Or the patrols are often multi-days, so they're out there for 4 days at a time. They come back after 4 days. They have to like take their phone, give it to like a technical manager. That manager has to like take out the SIM card, like plug in physically that SIM card into a computer, download the data, upload that into like a master system. So in many of these contexts, like the amount of data availability, just like and the level of like technological advancement is like falls far short of the context that we're more used to. So there's all these challenges of like delayed feedback. But that really gives us like ideas of thinking about what kinds of methodological directions we might want to go into. We have to think about like how to respond with batched feedback, and think about actions that are not just kind of like sequential day by day, but thinking of, okay, what is like a monthly goal, for example.
I appreciate the feedback. So it sounds like there's a lot of room for development in that sense. And that's another exciting aspect to this work. I have one more question I'm going to hand off to my friends, and I'm sorry to be taking so much time. The other question is very distant from your talk today, but related. And the question is, what is I'd like to hear about your academic pathway, the pathway that brought you to this genre of research. And the reason I'm asking is I'm thinking a lot these days about how do we do a better job of implementing the type of academic pathway that you followed so that our students the future professionals that we're creating are set up to solve the kinds of problems and deal with the computational research universe that awaits them and will be in my opinion, the major funding pathway for the next 50 years. How'd you get here? What happened?
So I guess it kind of sounds like, you're asking more about like the computer science and AI side rather than the like kind of like sustainability, social good type side. Am I understanding that correctly?
Kinda. I'm thinking more in general about computational research, right? And all aspects of that in everything that we do in higher education.
Yeah. So first, I think that like one thing that I want to emphasize is I think that 18-year-olds are quite savvy, and they have a sense of like, okay, this is, they're much more up to date on like technology and developments than I am, at least. So I feel like they are very good at kind of like keying in on those trends and the directions of where the job market are going. So I think we already see this in just like the explosion of people doing computer science and engineering majors and now the proliferation of all these additional opportunities like data science. I do think that like one thing that is extremely valuable is recognizing that like computer science and computational tools is not restricted to a specific discipline, but rather it will be increasingly embedded across everything else. Like now we have, computational biology, we have bioinformatics, we have computational precision medicine, we have like natural language processing for political science. So increasingly, like computational tools are essential toolkit for every other discipline. And at least when I went to undergrad, many majors had a statistics required class. So it's like you could take statistics for economists, you could take statistics for psychologists, you could take statistics for, I don't know, political science. And I think what we really need to see is we need to see data science for X, data science for biology, data science for neuroscience, data science for political science, data science for creative writing. Like we we really need to kind of be adaptive and give people who aren't just focused on engineering access to like this core set of data savviness and statistical knowledge and machine learning practice.
Yeah, you nailed it, and I so appreciate it. It affirms where I'm coming from. Here's a link in the chat where I'm coming from, and just an unabashed plug for this. But the point is, you are ideally situated to spread these words, and I'm grateful for you being here, and being a lot younger than I am. Because this is I couldn't agree more with everything you just said, and I'm going to quit talking and hand off to my good friends now that have had their hands up for a while. Thank you so
Awesome to see
much.
this book. Thank you for writing it.
Thank you, Jason.
Rita?
Yeah. So, great talk. I really enjoyed it. I think everybody has the burning question of what came first, the CS or the social good, right? And right
Yeah.
now it's almost like they're decoupled. But so was it the CS came first and then the social good? I mean, are you trained in ecology and all that, or?
No, I've never taken an ecology class or conservation science or anything like that. Those are very much things I picked up along the way. But I don't know, my story is that I was a computer science major who just like, always like loved the environment and cared about things. But I just saw that as like separate. I was like, okay, this is something I like do care about in my personal life. And then like professionally and academically, I'll focus on uh computer science. But then when I was figuring out, okay, well, what should I do as a computer scientist? I think, research is something that's exciting to me, but I don't really know, I don't have a specific direction I want to do research in. And then when I was doing a big breadth search, looking into PhD programs, I came across like a small handful of people working on sustainability applications. And it was just like that kind of marriage between like the cause and the thing that I was passionate about with the technical skills that I was building up. And I just said, oh, well, if I could do something that's kind of like, mission driven as well as technical, that was really the best of both worlds. So that was the direction that things came along for me. But I think, I might not have even gone to grad school if I didn't find these examples of people like working on the kinds of problems that I was excited by.
Yeah, that's awesome. Thank you. Thank you. So I have a question. So how much does like these snares are like they're pretty wide. I mean, like they don't discriminate between different animals. So how much does like community composition in a certain landscape feed into your your the what you're feeding into your models?
So community composition in terms of like the species
Yeah,
communities.
right. I mean, yeah, like the richness, right? I mean, richness, evenness of these species, right? These are really important. And there's really good, I would argue there's really good historical data for these sites on that. Does that factor into your?
Yeah, so we like as part of our predictive models, we are also taking in whatever information we have about animal densities and locations. So we explicitly factor that in as a covariate. And then I also briefly mentioned work that we did where we're also thinking about that integrating species distributions in our objective function. So prioritizing like more valuable species or more endangered species, for example. But I think a lot still remains to be to be done in terms of better understanding, like, some questions that folks were asking about earlier, which is like, what drives poachers? Like, what are they motivated by? Like, how do they make decisions? Because that would, like, recognizing like how they react to certain species, how they are able to kind of anticipate migration patterns and seasonal movement patterns, like that would be extremely essential. And I think this is the type of knowledge that like ecologists have and anthropologists have, and finding more ways to like bridge those communication gaps, but then also find ways to translate that like qualitative knowledge into technical formulations.
Yeah, and there's pretty good quantitative knowledge in that too. So yeah.
Absolutely.
So yeah, excellent. Thank you so much.
Of course.
And
I know we're at
what
time.
happened? You had your hand raised.
Sorry, yeah, I need to go to another meeting. But,
Okay, well,
yeah, but I
sorry we
had a
missed it.
question and an excellent task, and very good example of application possible with AI. The question I had was uncertainty modeling, because like with
Yeah.
poachers' behavior that you're trying to model, especially mathematical with minimax formulation.
Yeah.
Do you look at any distributional robustness, model or?
We haven't. So the only way that we've looked into robustness is the one that I shared when we're thinking about the minimax regret objective. So for that, we're assuming that we can define like some uncertainty space, and that we don't know what the distribution is across all of that. So we're not. If we did, then we could be thinking more about like, oh yeah, like expected value, like maximize expected reward. If we had like a known probability distribution over that uncertainty, but we think that it's hard, like that kind of prior is hard to have in a lot of realistic contexts. But I assume, based on your question, I assume that you might work on distributional robustness. So please help me fill in the gap of what I don't know.
Yeah, I think a little bit. So I work on power grid data and AI
Oh, cool.
applications. So yeah, we do deal with less data because we
Yeah.
don't have a lot of sensors in the power grid.
Yeah.
But because you're observing the behavior and improvement, right? So
Yeah.
you can compare that, how the behavior was for the poacher and what assumption was formulated. And by comparing that, you will still get less data, but over time, you can develop some kind of distributional behavior first, distributional characteristic first, and then embed into robustness, or adversarial uncertainty sets kind of model.
Yeah.
You can develop and integrate that. That also brings the second thing, like if you take this and start implementation, from the cold start, right? So you don't have any data. What kind of things can be, correlated with another problem set or another area?
Yeah.
And can you leverage some spatial correlation structure to do the transfer learning?
Yes, I think there's so much that can be leveraged in these kind of like spatial problems. And transfer learning is also, I think, a highly relevant line of work. Just thinking about like how can we build models that are generalized both, so we're not just like doing prediction for one park in isolation, but trying to predict over a broader set. That's really great.
Yep. Thank you. Thanks again.
Awesome.
Well, time is 11, therefore I don't want to take more of your time, Lily. I owe you my question, but I will send you those by email. I really want to thank you for accepting our invitation, and thank you for this wonderful talk.
Yes, really appreciate it. This is super fun. Thank you for this discussion. Great to meet you all. Thanks.
Okay.
Thank you.
Thank
Have a
you.
good day, guys.
Happy Friday.